A+ലേക്കുള്ള വഴി ഇനി തനിയെ തുറക്കാം. Subscribe to the Enclaps channel. Ring the bell button and open success. It's that easy.
Hello. Let us consider squares having sides 1 cm, 2 cm and 3 cm. The sides of the squares forming the sequence of counting numbers. Now the perimeter of a square is the sum of its sides, right? The perimeters of the squares will form another sequence, that is 4, 8, 12. If we examine these two sequences and name each term according to their position, then the sequence of perimeter will be as shown, that is 4, 8, 12 and 16. The term in a position is 4 times the number that representing the position, that is the first term is 4, second term is 8, third term is 12 and so on. In algebraic terms, if n is the number representing the position, then nth term will be the value, that is 4n.
Usually the terms in a sequence are written in algebra as x1, x2, x3 or y1, y2, y3 etc. So we can shorten the above rule further as xn is equal to 4n.
If we take the value of n as 1, then the term obtained will be 4, that is 4 into 1, 4. Similarly, the value of n is 2, then the term obtained will be 8, that is 4 into 2, 8. So by using the same procedure, any term of the sequence can be calculated. Then what will be the 50th term? That is 50 into 4, 200. Similarly, the 100th term will be the product of 100 and 4, that is 400.
If the sides of the squares are 1, 2, 3, etc., then the sequence of areas can be written as 1, 4, 9, etc. First term is square of 1, second term is square of 2, third term is square of 3 and so on. So it can be said that each term is square of its position. So if the position is n, then the term at that position will be n square. In algebraic terms, it can be written as xn is equal to n square. Now consider the diagonals of the square. The first square has a side of 1 cm, then it will have a diagonal of root 2 cm if we apply Pythagorean theorem. Similarly, the square having side 2 has a diagonal of 2 root 2 cm. So the sequence of diagonals can be written as root 2, 2 root 2, 3 root 2, 4 root 2 etc. By observing the sequence, we can say that multiplying the position with root 2 will give the term of the sequence. That is, for the first position, 1 into root 2 is the diagonal. And for the second position, 2 into root 2 is the diagonal. So in algebraic terms, nth term can be written as xn is equal to n root 2. So by using same procedure, the diagonal of 25th square can be written as 25 into root 2, that is 25 root 2. Now let us consider the squares got on increasing the sides by half centimeter. The sequence of sides of the squares can be written as 1, 1, 1 by 2, 2, 2, 1 by 2, 3, 3, 1 by 2 etc. Now to find the algebraic form, let us convert this mixed fraction into simple fraction. To convert mixed fraction to simple fraction, multiply denominator with the whole number and add the numerator. So simple fraction of 1, 1 by 2 is 3 by 2. Similarly, the sequence of 1, 1, 1 by 2, 2, 2, 1 by 2, 3, 3, 1 by 2 can be written as 1, 3 by 2, 2, 5 by 2 etc. Here in the sequence, the alternate numbers are fractions with denominator 2. The whole numbers in this series can also be written as fractions of denominator 2. That is, 1 can be written as 2 by 2 and 2 can be written as 4 by 2 and so on. So the sequence can be written as 2 by 2, 3 by 2, 4 by 2, 5 by 2, 6 by 2 and 7 by 2 etc. If we consider the numerator of the sequence, it is counting numbers starting from 2. The first numerator of this sequence is 2, which is 1 plus 1. Similarly, the second numerator is 3, which is 2 plus 1 and so on. So it can be said that the numerator of the sequence is the sum of position of the term and 1. For the first term, first position plus 1, and for the second term, second position plus 1, and so on. So in algebraic terms, it can be written as xn is equal to n plus 1 by 2, where denominator is always 2. The sequence of perimeters of squares is 4, 6, 8, 10, etc. To find the algebraic expression of this sequence, the relation of the term position and term must be obtained. First term is 4, second term is 6, third term is 8, and so on. From this, it is evident that the term position is added with 1 and multiplied with 2 to obtain the term. That is, 4 is 1 plus 1 into 2, where 1 represents the position. Similarly, 6 is 1 plus 2 into 2, where 2 represents the position. So in algebraic form, it can be written as xn is equal to 2 into n plus 1, where n represents the position. So if we want to find the perimeter of 50th square, it will be 2 into 50 plus 1, that is 102. The sequence of areas can be written as 1, 2 1 by 4, 4, 6 1 by 4, etc. As we did earlier, convert the mixed fractions into simple fractions, that is the sequence will become 1, 9 by 4, 4, 25 by 4, etc. Here the alternate terms are whole numbers and the remaining are simple fractions. Converting the whole numbers as fractions, we will get the sequence as 4 by 4, 9 by 4, and next 4 can be written as 16 by 4 and 25 by 4, etc. Here the numerator of this sequence are 4, 9, 16, 25, etc. These terms are squares of counting numbers starting from 2. The numerator of the term in first position is the square of 2, and again in the second position it is square of 3, and so on. And denominator is always a constant value, that is 4. So the algebraic form of this sequence can be written as xn is equal to n plus 1 the whole square by 4. So for the first term, for example, if we substitute n is equal to 1, we will get 1 plus 1 the whole square, which is 2 square, 4 by 4, which will be equal to 1. So similarly, all the terms can be obtained.
Let us analyze a problem by using 3 mastics. First, make a triangle by using 3 mastics. If we add 2 more mastics as shown in figure, then there is 1 more triangle. Again, if we add 2 more mastics, then there will be 1 more triangle, that is, there is a total of 3 triangles till now, correct? So in the first triangle there is 3 mastics, then for the 2 triangles we needed 5 mastics, and for the third triangle, up to third triangle, we needed 7 mastics. If we consider this sequence of numbers of mastics for each triangle, we will get a sequence that is 3, 5, 7, 9 and 11. For first triangle 3, for first and second triangle 5, for first, second and third triangle 7. If we consider this sequence of numbers of mastics for each triangle, we will get 3, 5, 7, 9 and 11. That is, for first triangle 3 mastics, second triangle 5 mastics, third triangle 7 mastics. So what will do to find number of mastics needed to make 10 triangles? We already know that for first triangle 3 mastics are needed, and for each of the remaining extra triangles 2 more mastics are needed. Then for 10 triangles, the first triangle need 3 mastics, and for each of the remaining 9 triangles 2 extra mastics are needed. That is, 3 plus 9 into 2, 21 mastics are needed. Then if the triangles needed is 51, we can use the same concept, right? For the first triangle 3 mastics are needed, and each of the remaining 50 triangles 2 more mastics are needed. So the equation can be written as 3 plus 51 minus 1 into 2. Here we subtracted 1 from 51 to find the number of mastics for the remaining triangles after avoiding the first triangle. So the equation can be simplified as 3 plus 50 into 2, that is 3 plus 100, that is 103. That is, for making 51 triangles we need 103 matchsticks.
In algebraic form, this can be written as 3 plus n minus 1 into 2, which is equal to 3 plus 2n minus 2, which is equal to 2n plus 1. That is, number of sticks we need to make n triangles is xn is equal to 2n plus 1.
3 ലക്ഷത്തിലേറെ വരുന്ന ചോദ്യോത്തരങ്ങൾ ഏറ്റവും കുറഞ്ഞ ചിലവിൽ സ്വന്തമാക്കുവാൻ ഉടൻ തന്നെ ഡൗൺലോഡ് ചെയ്യൂ Enclaps, the learning app.